On this occasion, we have Benedikt Altmann from Siemens, Lukas Kautzmann from AddUp, and Ansgar Mesh from Harting, and they're going to be talking about the 2024 AMIM project. So again, we're looking at how AM is being used to revolutionize mold production with conformal cooling, productivity optimization, and improved part quality. So, chaps, over to you.
Yeah, thank you. So we're going to present you a project we carry out this year with the AddUp, the company, with the colleagues from Harting who brought us the use case, and with the support of Siemens for all the software solutions we need to do the whole project. So we can start with our presentation. That's the thing. So to me, I'm the technical project manager on AddUp side. AddUp is a machine OEM, so we produce the powder bed machines and also DED machines. And we have a strong focus on the tooling segment, and especially injection molding, where we develop a lot of applications.
Yeah, hello, dear audience. My name is Benedikt Altmann. I'm from Siemens DISW. So for the software business, I work as a global pre-sales solution consultant for Additiv Manufacturing portfolio. And for this project, I was supporting our dear colleagues from AddUp in the software solutions.
Hello, my name is Ansgar Mesh, and I'm a development engineer at Harting Technology Group. And yeah, Harting is a global leading supplier for connectivity solutions. And yeah, this position is achieved with a high level of in-house vertical integration, as you can see here. And yeah, we have gained experiences according additive manufacturing and also cooling applications over the past few years by comparing different technologies. And yeah, the company is currently look into the feasibility of modern AM as a standard process for a specific series for our products. Yeah, let's now focus on our product targets. Yeah, the main goal is to increase the productivity of our molds by the reduction of cycle time. This results into an optimized machine capacity and also lower production costs. Additionally, we also want to enhance and guarantee a high quality of our parts in terms of higher product requirements and tolerances. We all know that that there could be a problem with shrinkage and warping. Otherwise, we also want to extend the life cycle of our AM molds by using new corrosion-resistant steels and focus on special maintenance of the AM tools. But yeah, what kind of parts are interesting for us and for this project? Let me introduce you our Han Echo connector, which you can see here on this picture. And yeah, this is one of our most important parts in our portfolio because we have a really high demand of parts every year. There are many different application areas for this connector. For example, transportation, energy, and also data centers. The high product requirements and especially the high voltage applications lead to large wall thicknesses up to 5 and 6 millimeters, which means we have long cycle times. And yeah, as you can see on this picture below, this specific connector is only a part of a big product family of the Han connectors. With this project, we want to show the potential also for other Harting products. Last but not least, the size of this connector is also really suitable for AM applications.
Okay, so a little bit on the AddUp side, where does that all come from? We want to push the injection molding application because we think that now is the best moment to go further because right now we have the right machine to do that, the FAMUP 350. We also developed a tool steel with corrosion resistance and good hardness, which is the Prindor HCT. It's like a standard tooling steel, but optimized for additive manufacturing. We have a lot of solutions for doing the designs now with the support of Siemens, especially in NX. And everything we have on that side allows us to go deeper. And for the project, we carried out the whole year. We had like 20 industrial companies who brought us their project so that we can work with them and develop the applications, but also a lot of technology partners who all brought their expertise, like the powder manufacturer, companies for polishing, for heat treatment, and all the suppliers of the parts for our machines so that we understand and go deep in this field. So now we're going to go deeper in the application we developed for Harting. We're going to give you an overview of the whole workflow we carried out, from potential analysis, conformal cooling design, simulation, until the post-processing we did. First of all, Harting came to us with these parts to manufacture the Han Eco part. Before we even start doing something, we have a closer look in the part. Is it useful to make it for AM? What are the benefits we can achieve? So here indeed it's conformal cooling, but can we even design it? Let's cross-check the wall thickness. Can we go close to the surface? And we have a first look to the economic viability of the project. How many will cost such a part? And then we start also thinking for serial production. What can we bring to Harting to bring this production in series, like hybrid manufacturing after doing the first prototype? The same for the cavity. So we build the whole mold, core and cavity, where we carry out the same study, where we're going to start a print for the first prototype to validate our concept. And then we can already start thinking for the next step. Maybe we do a hybrid manufacturing where we print on existing plates, or we scale that for faster production. So we consider all the possibilities in the first step. And then the interesting part starts where we start designing. So here conformal cooling, where you can see the conventional cooling a little bit how it's made. So it's drilled, it's not very flow optimized, and not very net shape. So here's the value we'll bring in conformal cooling. So we can design it close to the surface, flow optimized. We can do several parallel channels to have shorter channels, less heat difference in the part, which will ensure us shorter cycle time. We can show with simulation we will have a more homogeneous temperature field in the part, which will lead to less distortion, and will consume less energy because we have less pressure drop in our cooling channels, so a lower pump needed.
And at this stage, that's the point where the software jumps in.
Exactly.
And so Siemens, as software provider in general, not only for additive, but in the context of this application, has developed a dedicated tool to support our engineers in developing the conformal cooling. So basically what Lucas does is a certain set of features and functions he reapplies constantly in order to get such design done. And what we have is what you can see here as a screenshot is a very neat suite to just have a set of functions that supports you and automizes certain steps, just like phase offsetting and generating the tool paths, or channel paths in this case.
Exactly. And that's exactly the way we go for doing the conformal cooling design. So here in this field, we always start by giving the phase offset so that we ensure that all the channels are to the same distance to the surface. Then we can use planes to make intersection to design all the cooling paths. So here, for example, the offset was 4 millimeters and the diameter of the channel 3 millimeters, which is the biggest diameter I can use to go in a truncated zone. So this is the way we fix our diameter. Here for cooling channels, we design usually one, and here with the symmetry properties we have of the part, we can just repeat them, which will ensure us to have same length of the channel, same pressure drop, so the channels are balanced very well. And then we just pipe it to the inlet outlet. In this case was already given because the mold exists conventionally, so we use same inlet outlet. And we try to shift the inlet-outlet as high as possible so that we can have the possibility further to do hybrid manufacturing. So we carried out that design for the core and for the cavity. You can see it here in plastic printing. And when it's designed, we validate this also in NX with the tool. Sometimes we have to make sure that there's no area where the distance, the wall thickness between the channels is lower than here, for example, 1.5 millimeters, to avoid any leakage or that we have a leakage because of low wall thickness. So this is very easy with the tool, and it's very good also to show our customer that we took consideration of all the requests. Sometimes they tell, please give me 3 millimeter wall thickness. We can show it very easily with the tool. And then we can go in simulation a little bit.
Yeah, and so once the design is finalized and also validated in terms of printability as a first run, at the end of the day, the customers would like to know roughly, at least, what performance this, in that case, mold insert is about to give you in the production phase. And also, again, the approach for Siemens is to enable CAD engineers and designers rather than shifting everything that's related to simulation into the pure CAE space. Because we commonly see there's business units doing the designing, there's business units responsible for the engineering in terms of CAE simulation, CFD, FEA. And so we wanted to create a tool that addresses the skill set of a CAD engineer. So again, it's about automation. And what we have here, the CAD user does not have to interact with mesh types, mesh sizes whatsoever, boundary conditions, right? So it's pretty straightforward. It's like 5 features you only have to define here, and you can click on run in the simulation and you will retrieve results like velocity, temperature interaction, pressure drop, right? And that's a pretty easy and efficient way to give you some initial results for further enhancements.
Exactly. Here I show you the simulation results for the core and for the cavity. So we run both simulations with same boundary conditions, flow, temperature. And what we can clearly see here on the core is how homogeneous the cooling is now compared to how it was when it's drilled. We can also nicely see that on this side, where the cooling was more focused on this one, we can go very closer and be more homogeneous overall. And the same applies also for the cavity, where you saw the manufacturing of the conventional cooling. It starts and goes all around, which means very long channel, with directly split it in 2 channels to ensure same temperature profile in both cavities, so that we cannot say one cavity is slower than the other. So here we have very fast an overview and can say, okay, and show to the customer and tell him, simulation shows us that the cooling will shorten your cycle time. So here we know we don't see a very big hotspot where we should further tune our cooling. And then we can validate our cooling. Sometimes we have to, well, always we have to make sure that the cooling channels are not too close to the surface, which would lead to a massive increase of the temperature. We have to make sure that we will not go over 80, 100 degrees Celsius. So here we can nicely validate that. Here we are under 40 degrees, and we can also check the temperature difference we have between in and outlet. For both, we did a check for both, and we can also define the pressure drop. So here we know, no problem, we will not have any issue with the temperature. And then we can perform a cooling simulation to see the wind we will have. So here it's very obvious to see how fast now we are able to cool compared to the conventional one. And here just a picture of how it looks like after 6 seconds with the same scale. That's why it's all red, and I scaled them to both. And we can see nice blue homogeneous temperature in the cavity. And then we have to prepare the part for the print once everything is validated, and that's where Siemens also supports us.
Okay, almost my last part here. So yes, so you've done the designing, you've done the engineering validation using the CFD and temperature, so the thermal simulation here. And downstream the process, what you would do next is the print preparation. For the print preparation, we've done already the printability study prior to the CFD simulation, but you can do it also in the context of the print preparation, seamlessly connected within an X. So you go from CAD engineering, CAE validation down to the CAM, and could generate the print file directly and put it on the printer.
Here, I'll just give an example for the core. Obviously, we did the same for the cavity. So we define our maximum overhang angle. In this case, well, here on the picture, I put 45 degrees just to highlight it nicely. We know by experience in our channels, we print them in very good quality on our machine. There are no support needed for this kind of diameters, so no support. And we just easily see in this area, we have the 0 degree overhang. This, unfortunately, we cannot print very easily, so we just put some small support inside. We know we will be able to print. And then we can go in the printing part after simulation.
Right. And since we're talking about metal laser powder bed fusion process here, which is comparable to a micro welding process, what you will see here that the stresses induce a distortion on the part, so a deviation to the nominal contours. You can overcome these limitations, which would cause your part to be out of spec after the printing, by performing a so-called process simulation using the inherent strain approach here. What you would do there then is you have a dedicated calibration procedure to teach the software how to perform a simulation for that material on that machine using that process parameter. And once that's done, you run the simulation, and what you simulate here as a result, you get the distortion, you get the thermal impact on your part during the process, or the printing process actually. And as a last step, you would create a so-called pre-compensated model. So you would apply a certain deformation factor, deform your part that you actually put on the printer, slice and hatch. And that's also seamlessly done within our solutions.
And most of you may tell me experience. We know that in such kind of parts, we will not have too much deformation, but it's important for us also to validate it, to simulate it, so that we can know the max displacement we have, so that we can work with minimal extra material for machining. This is also then a big save for the end customer, who can avoid the rough milling and directly go in finish milling. Big time save. So that's why it's important for us to do these simulations. And then we can go on the machine and start the printing. As I said, with our tooling steel Printdoor HCT, developed for us from Swiss Steel Group. Corrosion resistance, the hardness is 52 HRC. We can push it slightly higher. Usually we work with 52 HRC, corrosion resistant, and a very good productivity in the print job compared to the standard tool steel. And on the machine, we'll work with the 4 lasers all over all the build plate to put as many parts as possible. Autonomous powder module, so that the machine runs alone. We just fill powder and it works in closed loop for best quality. And our monitoring system will allow us further to validate that everything was okay in the build. Here the pictures and the times a little bit of the production, so you can see the parts. They are also available on the booths if you want to, the AddUp booths if you want to see. And we print them in 77 hours, and here in 44 hours. This just, and in the validation, as I said, from the build report, we can validate everything was okay, temperature in the machine, O2 level in the machine, everything okay. And the 3D scan after the print, so less than 0.1 millimeter error, and hardness measured 52 HRC.
Yeah, I just want to give you a quick overview about the post process. And yeah, as Lucas already mentioned, the parts have been printed and heat treated at AddUp. And then we got the parts with a specific offset. And yeah, we did all the mechanical post-process at the Harting tool shop, such as grinding, milling, and different EDM processes. And yeah, as you can see, the first parts are already finished. And this is also the current project status. Next slide, please. And yeah, the next steps will be, of course, the sampling on the machine. And yeah, this will be really interesting to see the real results of this project. And then we will do the comparison to the conventional mold. And yeah, this evaluation will be also supported with CT scans of the articles and also with a thermal analysis of the mold. And yeah, I think already finished. Thank you very much for your attention, and yeah.